Hi, in this video I'm going to look at the centers of mass of various different shapes. If we have a piece of wood, nice uniform piece of wood, it's the same all the way along it, where would we expect the center of mass of that to be? Well, I think most of you would say that it's in the middle, and so it should balance about the middle point. Very, very nearly. You can see once it goes one way, another time it goes the other way. That was almost it. And there we have that the center of mass must be right in the middle of the plank. We say that all the weight appears to act at the center of mass, or we can consider the mass as concentrated all at one point, that point, the center of mass. What happens if we take a shape like this? We no longer have a uniform shape. It varies all the way up. What can we say before we start about where the center of mass is of this shape? Nice wooden spoon. Well, you can see that this is symmetrical about an axis of symmetry, which goes all the way horizontally along there. So we would expect the center of mass to be on that, assuming that the wood is of a constant density throughout. Otherwise, the only way we can find out where the center of mass is to balance it and see if we can get it to balance. There we are, just about perfect. No? So our center of mass is just at this point here on the spoon. No longer in the middle because we don't have a uniform shape. We can't guarantee that it will be in the middle, but even so, wherever the center of mass is, all the weight appears to be acting at that point because it's balanced by a single force back upwards, single force pushing up, and therefore we can think of all the mass as concentrated at that point. What happens if we take a sheet of cardboard? This we would call a lamina. To a mathematician, a lamina is a plane shape with no thickness. Of course, you cannot have something that hasn't got any thickness, but mathematicians can do everything. We would expect the center of, or the piece of cardboard to balance about the bisector there. We'd also expect it to balance about the bisector there. So let's just see if we can get that to work. Perfect. And very nearly. There you can see that it's just, there we are. We've got it. And so if it balances about those two lines, we would expect the center of mass to be right in the middle at that point where we can see the cross. Well, let's be ambitious. If the cross represents the center of mass, and we're saying that everything is concentrated at the center of mass, then we should be able to balance this thing about, perfect, on the center of mass. So whilst it is balanced on the center of mass, we can see that all the weight is acting at one point. All the mass appears to be concentrated at this point, the center of mass. Well, what happens if we take a slightly more complicated shape, a triangle? If we have a triangle, how can we find out anything about the center of mass? Well, let's look and see what happens if we start to balance it. If I balance this triangle, let's suppose I balance it with the vertex on the ruler, vertex on the ruler, and we're balanced. That is balancing about that line. Starts at the top and goes down to this point on the bottom side. Where do you think this point is? Well, it makes sense to think of it as the midpoint of the bottom line. That line then is called a median. From the vertex to the midpoint of the bottom side, or the opposite side, is a median. Well, if the triangle balances about one median, it really ought to balance about any median. So let's try this one. Perfect. And let's try this one. Not so lucky this time, but you can see that it's trying to, I got it, it is balancing and having a little bit of fun seesawing around. So that means that all three medians, the triangle will balance about each one. And seeing as we're assuming that the center of mass will be on the line of balance, that means that the center of mass will be on all three medians. And that says that all three medians ought to go through a point, common point. Well, if you look at what we have here, you can see that I have drawn all three medians. And without cheating, they did go through the point in the middle. I then measured various lines. The distance from the bottom up to the center of mass, which I've called G, is 6.4. I don't know if you can read that. And then from the center of mass up to the top is 12.8. Well, I don't think we need a calculator for this one. 2 times 6.4 is 12.8. So G divides the median in the ratio 1 to 2. Well, let's look at another one. If we take this one, then the length at the bottom is 7.7. Slightly more complicated for you to multiply that one by 2 because you have to carry. 2 times 7.7 is 15.4, and that is what the length of the top line is. Let's see if that works for the third one. For the third one, we have a bottom length of 8.6. If we double 8.6, we get 17.2, and 17.2 is the length there. So we have that the center of mass of a triangle is at the point where the three medians meet, and they do actually meet, and the center of mass divides each median in the ratio 1 to 2. And when it was balancing, we could see all the mass or all the weight appeared to act at one point, and all the mass we can think of as concentrated at that one point. That is what we really mean by a center of mass. The fact that the three medians do meet in a point is something which I have proved in the worksheet which accompanies this video. Okay, let's summarize the results that we've just seen. The center of mass of a uniform rod is at its midpoint. That's just common sense. The center of mass of a uniform rectangular lamina, or sheet, is at its point of symmetry. More common sense. And then something which is a little bit more significant. If you have a uniform triangular lamina, then the center of mass G is where the three medians meet. And it is always at a point on each median which divides the median in the ratio 1 to 2. Ratio 1 to 2. 1 to 2. So the G is 1/3 of the way along the median. It's also true that you can find the position of the median if your triangle ABC is at the points A1, A2, B1, B2, and C1, C2. then the center of mass is at the point 1/3 of A1 plus B1 plus C1, 1/3 of A2 plus B2 plus C2. We can summarize that just writing it as vectors, that the center of mass vector R is 1/3 of vector A plus vector B plus vector C. Okay, let's move on and have a look at this shape. This is a uniform lamina in the shape of a sector of a circle. The radius of the circle is R, and the angle at the center of the circle O is 2 alpha. The length of OG, where G is the center of mass, is given by 2R sine alpha divided by R by 3 alpha. 2R sine alpha over 3 alpha. This formula, if you carry on to M3, you will learn how to prove that there. But for the moment, we shall just assume that it is true. Okay, let's do a couple of simple examples. Find the coordinates of the center of mass of the uniform triangular lamina ABC. Well, let's sort out what we're going to do to find a solution. We know that the center of mass lies on a median and it's 1/3 of the way up. So let's take the median from C to the midpoint of AB. So we want the line which goes from M down to C. And G is going to be 1/3 of the way from M to C. And if you think of similar triangles or enlargement theory or anything like that, if we go, let's go the other way, 2/3 of the way, it's the same as going 2/3, 1/3. 2/3, 1/3. So in other words, if we're going 1/3 of the way along there, we go 1/3 of the way along here. Well, BC is 12, and therefore we go to a point, BC is 11 minus 2 is 9. If I take 1/3 of that, that is 3. From 2 plus 3, we get to 5. And so the x-coordinate of the center of mass is going to be is 2 plus 1/3 of the length of BC. That's 2 plus 3, that is 5. In the same way, we can look for the y-coordinate. It's going to be, well, we're starting at 1, and then we're going to move a distance of 1/3 of the way up. B to A is 6, 1/3 of that is 2, so we're going to add 2. That means we're going along 3 and up 2. So our center of mass, we reckon, is there. 1 plus 1/3 of BA, which is 1 plus 1/3 of 6, which is 3. So we have that the center of mass will be at the point G. Does that make sense? Is that 1/3 of the way along the median? Well, if we go from M to G, we go along 3, down 1. So that's M to G is along 3, down 1. If I now go along 3, down 1, along 3, down 1, you'll see that I have taken 2 lots of MG to go from G to C. So G is certainly on the median in the ratio 1 to 2. So G is the point 5, 3. Let's just see what happens if we use the other formula, that the vector r is 1/3 of the vectors a plus b plus c. Well, 1/3 of a is 2, 7, plus b is 2, 1, plus c is 11, 1, is 1/3 of 2 plus 2 is 4 plus 11 is 15. 7 plus 1 is 8 plus 1 is 9. If I do a third of that, I get 5, 3, which fortunately is the same point. Okay, let's look at another example. How can we find the coordinates of the center of mass of the uniform semicircular lamina, which is shown in the diagram? First, a reminder. If we have a sector of a circle of angle 2 alpha and radius r, the center of mass is at a point OG, where O is the center of the circle and OG is 2r sine alpha over 3 alpha. Well, if we have a semicircle, then alpha is pi by 2. 2 alpha is then pi. And so in this case, OG is going to be 2r sine alpha, sine pi by 2 is going to be 1, divided by 3 alpha is going to be 3 pi by 2, which equals 4r over 3 pi. 4r over 3 pi. Now we want to remember that whilst we go back up to the picture that we had, that the distance from the center of the circle to the center of mass is 4r over 3 pi. OG is 4r over 3 pi, where O is the center of the circle, not the origin. In this case, we can see that the radius of the circle is 1, 2, 3. And so I lost a bit of the pi. And so if r is 3, this is 4 over pi. So G is here, where the distance OG is 4 over pi. So that G, therefore, is x coordinate will be 2 plus 4 over pi. And the y coordinate will be 4. Quite easy. The results that you've seen today are in your maths textbook M2 on pages 39 to 44.